Okay, so this is problem 3.8, number 21. Which basically says, assume that A is an invertible matrix. And show that the inverse of the nth power of A is the same thing as the inverse of A raised to the nth power. The proof would be by mathematical induction. That would be your statement. P of n is that A to the n to the power minus 1 is the same as A minus 1 to the power n. The base case is, of course, P of 1 in this case. And just need to verify that that's true. Well, A to the 1 inverse is just A to the 1 is A, so that's A inverse, and that's A inverse to the power 1, just because the power 1 just means to write the symbol down correctly, and so that takes care of the base case. The inductive step is to assume, well, we'll do the standard kind of induction, assume that P of n is true, and prove from that assumption that P of n plus 1 follows. So we're assuming n plus 1. What we really need to do is show that this A to the n, the multiplicative inverse of A to the n plus 1 is the same as the n plus first power of the multiplicative inverse of A. So what I'm going to do is just look at a calculation, A to the n plus 1 times A inverse to the n plus 1. So that's really the product of those two matrices. And now I'm going to apply the definition of power of A to write that as A to the n times A in the first pair of parentheses, and apply the definition of power to this one to write that as A to the minus 1 times A to the minus 1 to the nth power. That's just applying the definition of exponent. Now I have A to the n times A inverse times A to the minus 1 to the n. Of course, we know that multiplication of matrices is associative, so the parentheses can be arranged. I'm going to write that as A to the n with no parentheses at all now, times A to the minus 1 times A to the minus 1 to the nth power. A times A to the minus 1 by definition of inverse is the identity matrix. So that gives me A to the n times the identity matrix times A to the minus 1 to the n. The identity matrix you can just erase. It has no effect on the product. And so we have A to the n times A inverse to the n, which is the product of the nth power of A and the nth power of A inverse. Our inductive hypothesis is that the nth power of A inverse is the same as the inverse of A to the n, which in effect means that that product, by the inductive hypothesis, is equal to the identity matrix. And this is because we're assuming P of n here. Now, that is what it means for one matrix to be the multiplicative inverse of the other is that their product is the identity matrix. And so, therefore, A n plus 1 inverse is equal to this, A inverse to the n plus first power. And this is by essentially the definition of what we mean by multiplicative inverse. Therefore, P of n is true for all values of n when you verify the problem.